to something else. It's like a VS West. Yeah. The high school students thought she just didn't test it. But kind of here, it's easy. You didn't think it was so, yeah.
All right, here we go. And let me flip the share just to show you all this question because it sometimes trips people up. All right. So this is walking us through an example of using the squeeze theorem. So we very often use squeeze theorem when we have trig functions because we know trig functions always bounce back and forth between two particular values. So sine of any ugly mess bounces between the amplitude and the negative amplitude. Now, since there's no number in front of the sine, the amplitude is just from -1 to 1. When we have it written as an absolute value inequality, this means that that sine graph, the absolute value of it is always less than or equal to 1. When we split it into the compound inequality, that's where we get the traditional between -1 and 1. Now, the next line is saying multiply through the compound inequality above by x squared. X squared is not negative for all x, so I can multiply through by it. I only have to worry about multiplying by negative numbers in an inequality. So since this is never negative, I can multiply by it. So -1 times x squared is -x squared. And then over here, we get positive x squared. So what this inequality means is the graph that we're trying to evaluate the limit of as x approaches 0 is squeezed in between these two graphs. Now, these two graphs, pretty much everywhere else, are not equal, but they do both shrink down to the same point. We've got the top parabola and the bottom parabola. So at x equals 0, they're both on the same point. And since this weird, crazy equation is always between those two, at that point where they're equal, then we know this graph also has to shrink down to that same point. Now, the graph itself, the function in the middle, doesn't actually equal anything at 0. It's undefined at 0, but the limit on either side is 0 above and below. So it forces the limit of this function to equal 0. But there isn't a way algebraically to figure that out. The only way to conclusively determine it is to compare it to something that we know what's going on. So the equation in the middle, they'll change what's inside the sine function, but all the rest of it is going to be identical. So the wording on this one and the format sometimes trips people up, but feel free to graph this and then graph the -x squared and x squared, and you'll see that it's always above and below this crazy graph in the middle, and that it'll shrink down to 0. All right, let's flip the share back. So what we're going to look at today is continuity. So when we hear the word continuity, what kind of stuff comes to mind? The word continuous. What does continuous mean? So it continues all the way through. So a lot of times this is like the word connected. When I think of like continuous, keeps going through, keeps doing its thing, it's like everything is all together. I literally think of a pencil doodling a graph because I've done the cool mathematical definition before. So intuitively, a continuous function is a function whose graph is nicely connected with no breaks or graphs. So it can be traced with your pencil without picking it up. So continuity is a property that we can talk about at a particular point or across the entire graph. So when a function is not continuous, then we say there's a discontinuity, and then we will define what type of discontinuity we have. So one of the types of discontinuities we can have is when we have a graph like this. It's coming along to a particular x value at a, but the function itself has a hole there. So on either side, it's meeting up at the hole, but the hole is empty. So that is still a discontinuity because technically I can't put my pencil down on that particular point. I can get really, really close, but eventually I'm going to have to make a little hop to continue. But since it's just one little spot, one little hole, we call this one a removable discontinuity. But one of our requirements for continuity is that the function must exist at the value we're looking at. So this function doesn't exist at a, so it cannot be continuous at a. For a function to be continuous at a point, the limit must exist there. So one of our qualifications of a limit existing is that the left and the right limits are the same. So in the previous graph, the left and the right limit are meeting up. In this graph, the left limit is a smaller value than the right limit. So the left and the right side are disagreeing, so the limit doesn't exist. But in the graph, this creates a jump in the graph. So instead of the tiny little hop because of the open circle, this one is a full out. You've got to change the value, the Y value of where your pencil is to continue drawing this graph. So we call this one a jump discontinuity. And jump discontinuities occur when the left and the right limits are not the same. Then for a function to be continuous at a point, the limit has to exist and the function value has to exist. And continuity requires that those two things be equal. So the left side of the graph and the right side of the graph have to come into the same value, and the point has to be filled in at that value. So this graph here is another removable discontinuity. It just happens to have a function value floating somewhere else. But that's enough to say it's discontinuous. So the full out book definition goes through those three pieces. F of A has to exist. The limit as x approaches A of f of x has to exist. And the two things have to be the same. So the third one is boxed here because if you can just prove this third statement, it proves the first two. So that's why we have the meme, me think why waste time say lot word when few word do trick. because mathematicians love to be pedantic. So here are the three types of discontinuities that we'll talk about, and we'll actually have to play around with the algebraic function and classify what type of discontinuity or if it's discontinuous. Like sometimes it'll be not exactly a trick question, but we're not always going to ask you about the spot in the graph where the weird stuff occurs. But most of the time, yeah, that is what we're talking about. So a removable discontinuity is when the left and the right limit equal, but the function value isn't that equal to that, or it's undefined there. A jump discontinuity is where we get a jump. The left and the right side are not the same. And then we can have an infinite discontinuity wherever there's a vertical asymptote. So even if the two sides of the graph are approaching the same infinity, like they're both going up, at that particular value, it's not considered continuous because there is still a jump. The function itself is not defined at that value. But we call it an infinite discontinuity to include the idea of it's going up and up and up forever. It's not just a hole in the graph, it's a full out asymptote. So our strategy for double checking continuity, first thing we're going to do is plug in the value and see if the function is even defined. And for most of our discontinuities, like this is the step it's going to fail at. So we're going to be able to really easily say, or quickly say, I should say, that it's discontinuous. But then figuring out what type of discontinuity it is going to require a little more work. So we plug in the a value, see if it's defined or not. Then we evaluate the limit. And this typically we're going to have to go through and do the limit on the left and the limit on the right, because a lot of these questions are actually defined with piecewise functions where it's a completely different formula on the left and the right side. And then the last step is make sure that your answers from 1 and 2 are equal. If they're equal, then that means we're continuous. So at the end, it says, if any step fails, the graph is discontinuous and you're finished. Sort of. You're finished unless the question says, what type of discontinuity is it? And then you got to play around a little more. All right, so our first function here, f of x equals x squared minus 4 over x minus 2. So this is all written in a line. It is very easy to miss that fraction bar there. But WebWork will sometimes write the equations this way. So don't assume just because it's all on one line that it's not division. So we're investigating the continuity at x equals 2. So our first step is to figure out, well, what's f of 2? So our function formula is x squared minus 4. So I have thing squared minus 4. And then that's all over thing minus 2. So now I'm going to fill in that 2 and all of my x blanks. All right, so 2 squared is 4. 4 minus 4 is 0. 2 minus 2 is 0. Uh-oh. So 0 over 0. What do we call that? Undefined usually. So does the function have a value at 2? We just called it undefined, so that means there's no value. So this right here, like it's definitely discontinuous. What we've got to play around with and see if it's infinite discontinuity, a removable discontinuity, or a jump discontinuity. So we answered the first question. Now we're just going to play around and figure out what type of discontinuity. So when figuring this out, what we do is we play around with the left and the right limit and see what they approach. So now we're going to look at the limit as x approaches 2 from the left of our function. So again, if I plug in the 2, I'm going to get the 0 over 0 again. But when I get a 0 from plugging in a number, that means that number that I plugged in is a 0 of that polynomial. So that means that that x value comes from a factor of that polynomial. On the bottom, x minus 2 is a factor. But this means the top, x minus 2, is also a factor of the top. So I can trade this out and figure out what it factors into. So one of those factors is x minus 2. What does the other one have to be?
+2.
Yep. So in my original function formula, even though they have the same factor on the top and the bottom, I can't cancel that out. The original function is not defined at x equals 2, and I need the original formula to stay as is to preserve that idea. But when we're looking at the limits, we can cancel these factors out. So now I'm just looking at the limit as x approaches 2 from the left of x plus 2. Now I can plug in the number. I get 2 plus 2, which is 4. Now, when I look at the limit from the other side, same thing's going to happen. Like, it's all the same work. So I'm just going to skip it straight to the x plus 2, x minus 2 factored form. So our left and our right side approach the same value. So our graph is not defined at x equals 2, but either side of the graph are coming into the same y value. So they're coming in to land at the same point. So if we think about sketching that, whatever the graph is doing, at x equals 2, either side is getting really, really close to 4. So I've got my open circle on 2, 4, and I know it's 4 because that's what the limit value approached. So this type of discontinuity, let's look back a bit. Is it a removable one, a jump one, or an infinite one? Yep, it's a removable. To get an infinite discontinuity when you're looking at the algebra, those limits would equal infinities. We didn't get an infinity, so it's not infinite discontinuity. The left and the right side were equal, so it's not a jump. So that leaves us with a removable discontinuity. And that's very often what happens when you get a 0 over 0 from doing the substitution. So what questions do y'all have on the way that one shook out? Now, the homework is going to approach these type of questions from several ways. A lot of them are going to do this kind of algebraic work, but they're also going to give you graphs to play with as well. Go for it. Yes, if it was only x minus 2 on the bottom and the top did not have x minus 2 as a factor, then we'd have a number over 0, which is an infinite limit. Because then it creates an actual asymptote. But it's when the factors in the top and the bottom like this and they cancel out, typically it's a removable discontinuity then. In some weird special cases, sometimes you can get a jump discontinuity instead, and we're going to see one example that does that, but they're really weird and really rare. So most of the time when you get 0 over 0, it's like, oh, this is going to be a hole in the graph. All right, now this one, we've got a piecewise function. So when x is less than or equal to 3, I've got this parabola, negative x squared plus 4. And when x is greater than 3, I've got this other function, 4x minus 8. So everywhere except 3, this function is connected and continuous because polynomials are connected everywhere. They're continuous everywhere. So our only question is at the breaking point. At 3, do these two graphs line up or are they not lining up? And this is typically how jump discontinuities are written because most functions don't have a jump discontinuity. It's very, very weird to have one formula that will do that. It's possible, but I can really only think of the one example we're going to have later that does it. So this one, the first question is, what's f of 3? So when x equals 3, we're being told use the top formula. So we're going to have the negative of things squared plus 4, and then we're going to plug in our 3. So 3 squared is 9. Then we have the negative of that. So we have negative 9 plus 4 would equal negative 5. So f of a is defined. But that's kind of a, yeah, there was an equal bar in those inequalities. So yes, it's defined. Now we want to figure out, does the limit exist? So here, whether we're on the left or the right side changes the formula we're looking at. So our left and our right limits have a real strong possibility of not being the same here. So the limit as x approaches 3 from the left is all the numbers smaller than 3. So we're going to use the negative x squared plus 4 formula. And that's going to equal the same negative 5 we just got by substitution. Now, when we're looking at 3 from the right side, this is where we flip to the other function, the 4x minus 8. But again, I'm just going to shove 3 in there and see what happens. So 12 minus 8 is 4. So does the limit as x approaches a overall of f of x exist? Why not? Because they don't agree. So the left limit exists, the right limit exists, but they don't agree on the value. So the overall limit does not exist. So we're failing at step 2 here. But when these guys are not equal, this is a jump discontinuity. So this particular graph, as we're approaching 3, on the left side, the graph is doing whatever, and it's coming down here to a negative 5. And then on the right side, it's up at 4 and then is doing a thing. So we even know that the point on the bottom is filled in. That's where f of 3 exists, but the right side of the function doesn't get anywhere close to that value. All right, so this next one is just a little more extreme version of the previous one, new formulas. But this is asking us to investigate whether it's continuous at x equals 1. And then if it's not, indicate the condition for continuity at a point that failed. That is horribly worded. If the function is not continuous at 1, indicate the condition for continuity at a point that fails to hold. Oh, okay. So all of this is saying, like, which part did it fail to uphold? Was it that f of a wasn't defined? Was it that the limit didn't exist? Or was it that the two were not equal? So the conditions are these things. All right, so our first step is still f of a. We're looking at 1, so f of 1. Now this case is set up, we've got the left side, the right side, and then we've got the thing itself. So if x equals 1, the function is just straight up defined to be 2. So f of a exists. It's defined, it's a number. All right, now we're going to check the limits. So we're looking at the limit as x approaches 1 from the left. On the left side of 1, we have the function formula 2x plus 1. I plug in my 1 there. 2 times 1 is 1. Sorry, 2 times 1 is 2, plus 1 is 3. Now we can already see, like, 2 and 3, these are not going to the same place. But let's see what happens when we look at the limit from the other side. So on the other side, we have this negative x plus 4. So we have the negative of 1 plus 4. Negative 1 plus 4 is 3. So here, these are equal, so the limit exists. The limit as x approaches 1 of f of x equals 3. So step 2 checks out. But step 3 is, do those two things equal? So is 2, 3? No. So this one is failing at step 3. So it fails condition 3. F of a does not equal the limit as x approaches a of f of x. Now, when it asks us to identify the type of discontinuity, when I'm looking at this graph, the left and the right side are meeting up at the same value. It's just the function didn't fill that hole in. It put the hole at a different point. So let's see, we're looking at 1. So our graph looks like this. It's coming in up to this point, this open circle at 1, 3, because that's what our limit approaches. But the function itself put a point at 1, 2 instead of filling in the hole at 1, 3. So the left and the right side agree, so this isn't a jump. We didn't get an infinity, so it's not an infinite discontinuity. So the only thing left is a removable discontinuity. All right, so now we've got one for you guys to try. So I've got x plus 1 divided by x squared plus 3x plus 2. That bottom thing does factor. So figure out if it's discontinuous or continuous at these x values, and then see if you can figure out what the type of discontinuity is. So just take a few minutes and try it out. Here, let me zoom in a little so it's a little bigger. And you can talk with your neighbor. You don't have to be silent about it. I mean, you could talk with someone across the room if you want, but that might be a little awkward. All right, is anyone still thinking about it, still doing some work? Or did y'all kind of get to a point where you're like, I think I know what I'm doing, or I'm stuck enough, I'd rather see it? Anyone still wanting to ponder a bit? All right. So while y'all were working, I waited a sec and then I also, did I not pause the damn screen share? So I was just up here doodling and y'all could see it. Yeah, all right. Embarrassing. All right. Well, I didn't actually write the conclusions down, but first step was plugging in the number. What do we get? We got 0/0. All right, cool. Discontinuous. Yes. But then what type of discontinuity? So that's why I checked the left and the right limits. They approach the same value. So that means that we have a removable discontinuity. And that's because the left and the right side are the same. Now, when we go to plug in -2, we get -1/0. That's also discontinuous. But when we have a number over 0, what we're going to see is that creates an infinity situation. Now, then the question remains, is it positive infinity or negative infinity? And you actually have to play around with it a little more. So when we plug in -2 from the left side, in my head, I plug in numbers left of -2, which like that's -2.1. It's a little more negative than -2. So if I had -2.1 plus 2, I'd get -0.1, and then 1 divided by -0.1 would be -10. So if I plugged in a number closer, I'd get a more negative number. But that tells me this one's going to approach negative infinity. So as long as you plug in a number that's close to -2 on the side you're looking at, the sign you get after that calculation tells you whether it was a positive or a negative infinity. So down here, when I'm approaching -2 from the right, like my work still looks the same, -2 plus 2, it's 1/0. But now I'm thinking like if I plugged in -1.9, that's to the right of -2. -1.9 plus 2 would now be positive 0.1. 1 divided by 0.1 would be positive 10. So this side's going to approach positive infinity. So that's one of the ways to kind of puzzle through, was it positive or negative? But the fact that we're getting the infinities means this is an infinite discontinuity. And whether the infinities are the same or are different, like we call both of those an infinite discontinuity. So we really could have even just getting the -1/0. That's like, oh, we got an asymptote, infinite discontinuity. Like we didn't technically have to go through the other two limit parts there on that half. All right, so what questions do y'all have on the way that one shook out? My work or my bad handwriting?
Since the limits are like, they're not coming to the same, wouldn't the limit not exist? Because you're getting negative infinity and positive infinity.
Yes. So the limit here does not exist. That's another reason why this is not continuous. But the fact that they were infinities, we call it an infinite discontinuity, yeah. But even just the first part where we got -1/0, that's undefined. That's enough to say, nope, not continuous, because at the number itself, there's nothing there. All right. And then we get this guy. So it looks like a nice little function. And the absolute value function itself is continuous. But when we do this kind of setup, the actual graph of this function is very weird. So we're going to make use of the piecewise definition of absolute value here. So the first step still, we're talking about continuity, is shove in the number and see what happens. So f of -3/2. So I have the absolute value of -4 times -3/2 minus 6, and then I close the absolute value. And then the bottom is the same thing without the absolute value. So it's really a question right now of what the heck is that number crunch up to be? So what do we get when we do -4 times -3/2 and then minus 6? Yep. So I got a 0 over 0. All right, so we know it's discontinuous. But we don't know if this is a removable discontinuity or a jump discontinuity. Probably not an infinite discontinuity, though, because we got 0 over 0. For the infinite ones, we usually get a fixed number over 0, like a non-zero number over 0. So here, we got to look at the left and the right limits, because it looks like the factor is the same on the top and the bottom, but which side we're approaching from changes what the absolute value does. All right, so I'm going to switch up the order here. I'm going to do the positive side first. So the limit as x approaches -3/2 from the positive side. So when we're on the positive side of a number, that absolute value is just going to be the thing itself. So I can just write this as the -4x minus 6 over -4x minus 6. And then they completely cancel out and I get +1 because it's exactly the same thing on the top and the bottom. But when I do the limit from the other side, so we're still approaching -3/2, but now I'm looking at the negative side. Now I'm plugging in numbers that those values, after I crunch it up, it would be negative inside the absolute value. So the absolute value says, oh, you're negative? No, 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 no. I want a positive result. So I'm going to change your sign. So algebraically, what's happening here with that minus sign on the limit, because we're on the left side, let me put it there. We're going to have the negative of -4x minus 6 on top. And then it's still just -4x minus 6 on the bottom. So the factors cancel, but because we're on the negative side of our 0 value for the inequality, the fraction actually ends up equaling -1. And the graph of this particular function is actually rather silly. So it turns out, regardless of what x value I pick, any x value I pick that's bigger than -3/2, I'm going to get a +1 for all of those x values. So let's put in our -3/2 here. So everybody over here, it just equals 1. Now, when we're on the left side of -3/2, like if I plug in -2, like -4 times -2, Did I do those backwards? I did do those backwards, didn't I? -4 times -2 would be +8. 8 minus 6 would be +2. So we would have +2 on top. The bottom would be 2 on the bottom. Yeah, I did them backwards. I failed to account for all the negatives that were inside the absolute value. I should have actually plugged in a number to the right, like -1. -4 times -1 would be +4. 4 minus 6 would be -2. And then I would do the opposite of that. All right, so I had which side was positive and which side was negative backwards, but the fact that the absolute value was messing with the sign in there, so they were going to do different things on either side, was creating this jump discontinuity because we can see the value is changing from 1 to -1. Now, for identifying discontinuities, doing these questions where you're working it from the algebra side is a lot of work and takes a fair amount of time. So we usually don't put this kind of detail-oriented question on the test because it just takes too much time. It's not that y'all can't do it, it's that the time you spend doing this, we would rather you showed us other things. So that's why the homework has a bit more focus on this algebraic side of discontinuities, because we're not going to put that on the test. But the thought process behind it, working this algebra, is still a useful skill to practice. It's getting you thinking about what are the different sides of the graph doing. And I think there might be one homework question that has an absolute value, but like we definitely don't put absolute value on the tests. Like it's a lovely look at this weird shit in class. It's not good for a test question. It's just a little too weird. So all that being said, like I'm trying to say that to reassure you, when we write the test, we are not trying to screw you over. I know it feels like that sometimes, especially with some professors you have, and some professors are actually assholes like that and will write tests like that. And someday maybe I'll have the ability to fire them for doing that, but right now I don't have that power. There is, strangely enough, a logic behind it. It's still a dickish logic, but they're thinking like, well, if you can't handle this weird question, then you can't handle math, so you shouldn't continue on. And it's like, that's like saying I'm not allowed to drive because I can't parallel park. I couldn't do the one little tricky thing that everybody screws up, so you're saying I'm not allowed to keep going in math? Yeah. I don't know if that makes sense or not, but now something like this I could see us putting on a test. I don't remember if we do or not, because it's a like argument of how much time it takes. But there's definitely, these are all over your homework. And the structure of these sometimes really confuses people. I think in part because the A value is like showing up in a spot, and then we also have A in the definition, and they're two different things. So when x is less than or equal to 3, our function is ax squared minus 6. When x is greater than 3, Our function is 8 minus 50x over 3. So this function is continuous almost everywhere. For any value of a I could pick, ax squared minus 6 is continuous everywhere. The other function is just a line. A line is continuous everywhere. As long as it's a function, it's continuous. What we're asking is, well, what about at the boundary point? The point where we're switching from one function to the other. Do those two sides line up, or is it a jump? So right now, that ax squared minus 6 could be almost anything. Like changing that a value shifts the graph around quite a lot. So what we're looking for is, what number do I have to make that a so these two graphs meet up? So it's really focusing in on that left and right limit equaling the same value. So the limit as x approaches our boundary point is 3. So I want to look on the left side, and I want to make sure that equals the limit on the right side. So I'm trying to force continuity. So I want this setup to be true. I want the limit to exist. So I want the left limit to equal the right limit. Now, when I look at this, my left side of 3, that's when x is smaller than 3. That's my first function formula. So I'm going to plug that formula in. So my f of x is this, ax squared minus 6. Then my other side, when x is greater than 3, my function formula is that 8 minus 50x over 3. I still have the limits in here. And I'm still saying these better be equal. Now, when I'm trying to evaluate this limit as x approaches 3 of ax squared minus 6, or you know what, let's jump to the right. So the limit as x approaches 3 from the right of 8 minus 50x over 3. What would I do to calculate what this limit equals? It's like, what's the first thing we try with limits? Plug in the number. So let's see what happens when we plug 3 into that function. So 50 times 3 divided by 3 is 50. 8 minus 50 is negative 42. So I plugged in the number, did the calculation. I have a numeric answer on that side. Same idea works on the right. We're going to plug 3 in for x. So this is a 3 in there that's being squared and multiplied by a and minus 6. So 3 squared is 9, so I can write this as 9a minus 6. So I'm just taking that same result I got and I'm just recopying it over here. So 9a minus 6 equals negative 42. Can we figure out what a is now? Yep, this is an equation we can solve. So I add the 6, that'll be negative 36 on this side. And then divide by the 9. So my a value is negative 4. So when I make a negative 4, that's going to force these two graphs to meet up at the same point. So that's the value of a that will make the function continuous. Any other a value and there'd be a little jump. or a big jump if I made it really big. So look at the structure of that one. Like, our whole purpose there was figuring out what a value makes our continuity definition all true. So the function was going to be defined because when x equals 3, we're using one of the particular formulas. We just needed the left and the right side to exist and equal that function value. Now that we have an a number, they're all true. How am I doing on time? Let me scroll a little bit. All right. I am going to skip these. So this one here, there's the possibility of more than one a value that would make it continuous because you end up solving a quadratic. You may have to use the quadratic formula to solve it. But there are some questions on the homework that do this split of two different variables in there. So there's an a variable and a b variable inside this wonky piecewise function. So this is saying there's values of a and b that will make this function continuous. So we're going to assume it's continuous and use our definition of continuity and set up our left and our right limits to equal. So our question points are at -5 and at -4. So my first half here, the limit as x approaches -5 from the left. The left side is -ax plus b. Yeah. Sorry. All right. So our left side of -5 is that -ax plus b. Our right side of -5 is the x plus 6. And then we're also setting up the equation around -4. The left side of -4 is the x plus 6 function. The right side is just equal to a. So the limit as x approaches -4 of a constant value is just that constant value. So this side is just straight up a. This other side, now I've got x is approaching -4, and I've got an x position. I can plug that in. So this is -4 plus 6. So I get a is 2. Now over on this one, I'm going to have the negative of a times -5 plus b. And this is going to equal -5 plus 6. So negative a times negative 5 will be positive 5a plus whatever b is, and this is going to equal negative 5 plus 6 is 1. So I've evaluated my limits by plugging in the x values, and I have two equations. Now, it turns out one of my equations is straight up telling me a value. So that's like one part of my answer straight away. But since I know a is 2, I'm going to shoehorn that in here for a, and then finish out the math to figure out b. So I've got 10 plus b equals 1. I minus the 10 over, so my b is going to equal negative 9. So anytime we're playing with those piecewise functions for continuity, it's just setting up your left and your right limit at any of the boundary points. Now we have a kind of couple interesting corollaries. So one of them is that, instead of reading all that, we can pass a limit into a continuous function. So when I'm looking at the limit of one function composed inside another, as long as I know those functions are continuous, which pretty much means if it's a function you've seen before, it's probably continuous almost everywhere. Most functions are actually continuous everywhere. Like our trig functions, rather, our sine and our cosine functions are continuous everywhere. Our other trig functions have vertical asymptotes, so they're continuous almost everywhere. As long as your limit value isn't at an asymptote, then you can pass the limit in and keep doing the work. So when we're evaluating something weird like this limit as x is approaching pi of the sine of x minus sine of x, we can just shove the limit inside and then calculate inside and then backtrack what happens outside, the sign of that result, answer. So this is going to be the same as the sign of the limit. Of that whole crazy mess. And now we can just pass in that limit as x approaches pi. We can just plug pi in. So pi minus the sine of pi. That's x approaching pi. So the sine of pi, sine starts at 0, goes up to 1, back to 0. So the sine of pi is 0. So pi minus 0 is pi. So this is the sine of pi, which is back to 0. Now, this is something we kind of already intuitively do, just from our limit laws, knowing that the limit like distributes across addition, subtraction, constant multiplication. Like a lot of people will just automatically assume this thing works without it like being formally stated. So basically it works as long as we're not looking at a weird asymptote. Now we do get another theorem in here. We're not going to study it like it's not on WebWork, but it is kind of interesting. So if I've got my first part of my graph comes and stops here at my x equals a, my function value f of a. And then I know over here at b, my function value is f of b. So if I tell you my graph f is continuous, what do I have to do for that in between question mark value? Like, what do I know for sure about that in between area? Does what have to be 0? So you're saying like we'd have to move the 2 points together? Okay. So that's one way to think about it, and that's actually like what happens with our definition of the derivative. So that's actually a really normal like thought to have of moving the points. What if I told you though those 2 points are like fixed in space? I can't move them. What I'm trying to do is continue the graph in between. So like it's kind of like I had a picture of the graph and then I spilled coffee in the middle and it all like went to shit. So I've got this like I cleaned up my coffee, but now I have this blank spot and I'm like, well, I know it's continuous, so how can I connect the dots?
You have to make the function equal at A and B.
So not move them, like we're not going to change the values. So the function has to start at A and finish at B. And it's starting, the y value is starting at f of A and the other y value is f of B. So I literally have to connect the dots. So when we connect those dots, like, you know, the easiest is straight line. But I could, like, if I thought this graph was a little more like smooth, maybe it connected like that. Or maybe I had an ugly piecewise function and I'm like, no, it does this. But the point is, any which way I fill in my coffee stain, I'm moving through all of the y values between f of A and f of B. And I'm moving through all of the x values between A and B. So every x value has some corresponding y value. Now, I can't guarantee you when the x value hits the y value, but I know for sure that every y value I can pick between f of A and f of B has some x value that corresponds to it because it's continuous. Now, it might be like that upper one I drew where I squeezed in all those weird y values at the front and then I just flatlined it for the rest. I can do it like that. It's continuous. Like my drawing's bad, but you know, if we make all those corner points line up, it works. So this theorem, the intermediate value theorem, guarantees us that if I know a function is continuous, I have to hit all the x values and all the y values in between any 2 points I know are on the function. So Chris did it's a bad math joke. Why did the chicken cross the road? The intermediate value theorem. Because at one point we knew the chicken was on one side of the road, and sometime later we knew the chicken was on the other side of the road. So why did he cross it? We don't know, but we can't say for sure he crossed it because we assume his path would be continuous. So some point in there, he was on the road and crossed from one side to the other. It's a very silly math joke, but you got to understand the intermediate value theorem to get the silly joke. But one of the ways we utilize that is if we have a really ugly function, like figuring out what the graph of this thing is not something I can intuitively do off the top of my head. That is a cubic function. Cubic functions have really weird shapes, and you have to do a lot more work with them to be able to produce that graph out of thin air. But if my question was, between the interval from 0 to 1, does that graph cross the axis? So if I plug in 0, I'm going to get 1. If I plug in 1, 1 minus 1 is 0, minus 3 is -3, plus 1 is -2. So I'm going from 1 to -2. So somewhere in there, I have to cross the x-axis. So I have to create a 0 somewhere between 0 and 1. Now, I don't know where in between there. It could be some disgusting number for all I know. but somewhere in there for sure is a 0 because polynomials are continuous and I've got one y value above the axis, the other y value below the axis. So in later math classes, like sometimes we use theorems, like this is getting close to structuring a mathematical proof. All right. There's just our summary at the end. So I did create a writing assignment for today. So if you go into WebWork, let me flip, wrong button, flip the share. Module 2, it now says writing assignment for section 2.3. And if you look at it, hopefully it loads the limits here. If it does not, there is also a PDF link that will load the same 2 questions in a PDF. If you want to print the PDF, that should leave you some space to work each question. Otherwise, you can write those down on a piece of paper and work it out and then turn it in. So if you don't have access to a printer, like it's this entire semester, we have to make everything in our courses accessible. So this is an HTML file, so it's accessible via screen reader. So I have to do this for everything, including the notes. I'm going to hate myself this semester because I have to do it for all the pre-calc crap too. So, but it's not just math. All the courses are doing this. So you're going to start to see the format get a little weird in some of your Canvas stuff. All right, but if you have problems accessing it, like email me. It is due at the end of the day today, a PDF upload. So. And y'all can work together on it. It's not like a quiz, just everyone has to turn in their own work, their own handwritten work. Gonna hit the stop share on that. All right.
The immediate value theorem.
Mhm.
It was actually about the chicken crossing the road joke. It was that we know the chicken is here on the other side of the road, and then it has values on the other side of the road. They had me thinking about like, does it just have like, if you draw a function, does it just have to be within those bounds, or is there any kind of like reasonable path it should take?
So when we're, oh, real quick. If you go into Jonathan on Canvas, the first like orientation module, I think it's the second to last one now, one of them should say GroupMe, and that should get you the GroupMe link. Cool. All right, I'm gonna end this so it'll start doing the, yeah.